So we want to talk about most of the concepts that are in sheet 2. So we talked about the sequences already, but then we'll just cement as we do the examples that are there. And then we also talked about the there's something that we left out that I want to talk about the limit by definition. As we wait for the other guys to come. This is the epsilon delta definition. So we'll look at question 8a, where you want to evaluate the limit. You want to show that the limit as x goes to 2 of a quadratic x squared plus 4x minus 5 is equal to 7. Now, whenever you're dealing with a limit by definition, the limit is already given. You are told that the limit for this is 7. Your job is to show how, or if you agree that it is 7 for sure, why are you agreeing? To give evidence. So we understand that the procedure here demands that we show so we need to find a delta.
Oh, I thought you were talking.
So that so your target is always to find a delta so that the x minus 2 being as x approaches 2, this guy should be less than delta. So when this is the case, then we demand that x squared plus 4x minus 5 minus 7 to be less than epsilon. That's how we call it epsilon delta definition. So whenever the x minus 2 is less than delta, we demand that the other situation also must hold. So you then start with this one. You first have an idea of what the delta is before you use it. So you first find the delta and then use the delta to show that the other situation holds. So we get x squared plus 4x minus, that becomes minus 12, is less than epsilon. This is simply telling us that if we do the squaring here, the factorization, we can use 6 and 2. So we have x squared minus 2x plus 6x minus 12 is less than epsilon. So this will be x minus 2 plus 6x minus 2 is less than epsilon. So that we get x minus 2 x plus 6 is less than epsilon. Now, we already have an idea that x minus 2 is less than delta. So now let us assume that delta is equal to 1. We always want to assume delta is equal to 1 because it has an easy approach towards the leading us to getting to the bounds that we want on the other side. So when delta is equal to 1, then we'll say, okay, then x minus 2 becomes less than 1, which is simply telling us that -1 will be less than x minus 2, which is less than 1. So now we can throw the 2 on the other side. So we'll have, on the other side, you will have 1 is less than x, which is less than 2. Like that. And then here we want to remain with only x minus 2. But we still have x plus 6. So now we are forming the x plus 6 using the fact that we have here. So add 1 plus 6, x plus 6, 3 plus 6. And then now we'll have 7 less than x plus 6 less than 9. So now we know that, oh, x plus 6 is just less than 9. So now we're going to use, since we want less, so we'll use the number that is bigger than x plus 6. So we'll say, this means that we now have 9 x minus 2 less than epsilon. And then the 9 can come out. So we have this less than epsilon. So that x minus 2 is less than epsilon over 9. So we want to say, oh, why can't we let delta then be equal to epsilon over 9? So we're getting there. So now I'm saying our delta is epsilon over 9. Though we know that what we have done here is initially we had the delta is equal to 1. Now we're saying a delta is epsilon over 9. So we can dodge by saying, oh, we will get the minimum of 1 and epsilon over 9 for the delta, which is clear that the minimum value between these two is epsilon over 9. When I say minimum in the brackets, I mean between these two numbers, which one is the smallest? Of course, epsilon over 9 is the smallest. So that's why we're saying, so our delta is going to be this one. Now, after you have found the delta, then you need to show that that now the limit is equal to 7. Normally, when you get here, you assume that you've done the right thing and you're done, but we are not yet done. We need to prove that that is the limit. Any issues on how we reach here? Because we expect this thing to use the death method to show that this is the limit. Okay, no question. That's okay. Let's just now get the proof of how that is the limit. We complete the setup. So now we say to prove, we must be given that epsilon is greater than 0. Then we let delta be equal to the one we have found, epsilon over 9. Then we are saying x minus 2 will be less than epsilon over 9. So that if we multiply, we're going to have 9 x minus 2 is less than epsilon. But then we must build back because we want to get to this one. We want to arrive at this one. So when you get there, Of course, this has happened after we had assumed that in our initial case, the delta was what? The delta was 1. Remember, we made this assumption. And I want to use the same assumption that we used there to get back. So we're building back now from down, going up to the question. Okay, but then coming, this happened when we said x plus 6. So x plus 6 is less than 9. So we made that assumption from here. So we think that this is the solution here. So we still use it back. So that now we get x minus 2. And then we bring back the product. X plus 6. So this becomes, since this guy is less than 9, so this becomes less than 9, x minus 2. But remember, we're saying this guy is less than what? We're saying this guy is less than, epsilon over 9. So which is just equal to epsilon. So now it has turned out that x minus 2, x plus 6 is less than epsilon. And if we expand here, we end up getting the whole quadratic, which is x squared plus 4x minus 12 less than epsilon, which is x squared plus 4x minus 5 minus 7 is less than epsilon. So it holds that whenever this is the case, where this is our delta, we end up having this be less than epsilon. Hence, shown. So this is what is expected of you when you're asked to show that this is the limit. You do it in 2 parts. The first part is to get the value of delta. The second part, so the first part is to find delta. You first find delta. After you find delta, in the second piece, you now use your delta to show that the limit is indeed 7. So this is what it means. This one. Still don't have questions, right? Sorry.
Yeah, it's clear, sir.
All right. Let's move. So I'll leave D for you to try. And then we move to 9. I've given you this as a task, so we just make sure that we count it down. The ln of sine squared x over the ln of tan x. So here we said if you substitute the zeros, you will get infinity over infinity. So this is infinity over infinity. So it qualifies to be under L'Hopital's rule. So it means that we're going to have the limit as x goes to 0. Then you differentiate. So when you differentiate up there, the derivative for sine squared is 2 sine x multiplied by cos x over, because it's coming from ln, we need to divide by sine squared x. So now I'll write sine squared x as sine multiplied by sine over, you differentiate term, you get sec squared x, and then over the whole term. After that, you have the limit as x goes to 0 plus this cancels. And then you have 2 cos x, that is cos over sine. So let me not change anything. Let me write it as cos over sine x. And then the piece down, I want to write it as tan x over sec x, over sec squared x. But then we also understand that this is just the limit as x goes to 0 plus 2 cos x over sine x. And then tan is sine x over cos x. And then since you have, we are multiplying by 1 over sec squared, and sec squared is 1 over cos squared, so that cos squared is going to be in the numerator here. Over 1, if you like. So we have this and this one cancelling, this and this one cancelling. So we have the limit as x goes to 0 plus of 2 cos squared x. And then now you can substitute where it's x, you put a 0, so you get 2 as the limit there. I guess that's okay. And it also attends to part B, so that we skip part B, we do part C. Does it? Silence is the same thing as acceptance. So we skip it, we go to C. The limit at x goes to 0 plus. Again here, ex minus 1.
So
Now to
you
the power.
can bring back the previous board. I didn't finish copying. Okay, thank you. We can proceed.
Okay. So we say that if you place a 0 here, you're going to have 0 to the power 0. So 0 power 0, you will let this be equal to y, the limit to the power sin x, and then apply limit. And when you apply limit the other side, limit goes inside the limit, and then it drops the power, and then limit of ex minus 1, like that. And then now, if you place zeros there, again, you're going to get mean of 0 is not defined. Assuming that you cannot do that, so you write this as the limit as x goes to 0 plus over you can do it place down. So let's place sign down. The limit ex minus 1, and then write it as 1 over sin x. Like that. So let's see. One step. We now need to differentiate both parts. So we have the limit as x goes to 0 plus. There we get ex over ex minus 1 multiplied by sine squared x over minus cos x. Now I've differentiated the denominator in such a way that you use quotient rule and then you flip it upside down. So what we have now is the limit as x goes to 0 plus ex multiplied by sine squared x over minus ex minus 1 cos x. So again, if you place zeros there, I will get 0 over 0. So we differentiate further. So we have the limit as x goes to 0 plus ex multiplied by sine squared x plus the derivative of sine, that is 2 sine x cos x ex over, we differentiate down, we have minus ex and fix the cos x, and then we have, so now we differentiated this one, we fix the other one. So now we're going to fix this one and differentiate cos. Now differentiating cos produces a negative, so we have plus ex minus 1 sin x. At this point now you can substitute where there is x, you take 0. So we're going to have 0 up there over negative 1, which is going to give us a 0. That 0 we have found is in y. So again, we apply the exponentials so that we get back our y. So we have y is equal to e to the power 0, which is equal to 1. So the limit as x goes to 0 plus of ex minus 1 to the power sin x is equal to 1. Like that. Next, if there are no questions, we now move to the sequences. Any questions? You guys don't like asking. We'll go to question 10. The first one, we are given an. So an is given to be negative 2 over 3 to the power n. Now we have a nice theorem that says that if the absolute value of x is less than 1, then the limit as x goes to infinity of that x to the power n is equal to 0. If the modulus of x is less than 1, then you have the limit as x goes to infinity of x to the power n equals 0. If we get the modulus for -2/3, we'll notice that we are getting +2/3, which is indeed less than 1. So then the limit as n goes to infinity of -2/3 to the power n is equal to 0. So we simply apply that principle, yeah? And then the second one, so these are sequences, so you must be a bit careful. The power n are n/n plus 1. So we want to get the limit as n goes to infinity of -1 power n/n plus 1. So this is going to be the limit. Remember the limit, if you're having product, you can split and do the limit for product. So we'll have the limit as n goes to infinity of -1 power n, and the limit as n goes to infinity of n/n plus 1. Now you understand that this limit here um, can easily be found. Okay, so here we're terming convergence. So I'm saying this guy actually converges. This guy converges to 0. Now this limit here converges at 1, but the other one diverges. So it means that altogether an diverges. Because of the -1 to the power n. So that one will keep on operating, -1, 1, 1, -1, 1, -1. We can't say it converges to 1, I mean to infinity. So just if diverges to infinity, just say this one diverges because its divergence is not straight. So we have the convergence multiplied by the divergence sequence. So it becomes divergent. So even the limit here doesn't exist. And then C we have AM, that is n, the sine of 1/n. What's the comment? So again, you want to check the limit as n goes to infinity of AM, which will be the limit as n goes to infinity of n sine 1/n. And then you write this to get the limit as n goes to infinity of sine 1/n. Then you write that n as 1/n. So if you let your n, if you let x take up the base of 1/n, what you end up having is the limit as x goes to infinity of sine x over x. Like that. And then here you can use n2 that you have And we have the squeeze theorem. Since sine is bounded by 1, so we'll have -1 over n this side, less than sine x over x. So I'm putting x here, which should be bounded by 1 over x. Because the numerator is bounded by 1 and -1, so the denominator then be bounded in the place x inside the other side. Now, as x goes to infinity, this guy converges to 0. This guy converges to 0. By the squeeze theorem, this limit here becomes 0 because the side are they all converge to 0. And so that breaks down into the 0 place. So we have that bounded by 0. And so we say this converges to 0. Oh, boycotted, and there are so many messages in my inbox. So the part that comes now down that is more critical for this. Okay, so I think you can't go further. Because so many people have reported not that they are busy, but that they don't want online. And only 4 of you are in attendance. I'm the 5th one. It will be hard for me to teach. That's why I've avoided to go in depth. So I've no option but to have maybe 2 hours class tomorrow. And also Saturday as well. So we just will end here.
We end here, sir.
Yeah, we end here because out of the
Oh, so
9.
this now we are
Hello?
epsilon.
Which one?
The epsilon one, yeah, that's this one.
This one.
Yeah, so yes, the same one. These conditions are given
No,
where you have said the absolute of x minus 2 is less than this one is. Yeah,
this.
where you are pointing.
Yes, this one.
And how did we come up with this condition?
So the definition of epsilon and delta states that x minus this value here should be less than delta, whereas the function inside